Hello all. In the video series of PCA, this is our second video and I will cover the objective function for principal component analysis in this video. So mainly I will cover these topics: why we need the principal component analysis, what is the geometric interpretation of the principal component analysis, and what is a mathematical formulation for principal component analysis, right? So why we need the PCA? So PCA is nothing but a dimensionality reduction technique where, let's say, if we have a d dimension of data, we will convert into d dash dimension of data where d is greater than d dash dimension, right? When I say the dimension of data, it's a feature of data or variable of data, right? So reducing the number of variables in the data, right? Let's talk about geometric interpretations. So let's say if I have one data x which have n data points and have two features f1 and f2, and its scatter plot looks something like this, right? Now if for some reason we have to drop one feature out of feature f1 and f2, so we have to answer these two questions. First is which feature to drop, and second one is why to drop that feature. Why to drop that feature only. Right. So to answer these questions, we have to look at the spread. We have to look at the spread of data along the features, right? In mathematical terms, it's a variability or variance of data along the axis, along the feature. And in very plain English terms, it's a information of data along the feature, right? Now if you will see the spread of data along feature f1 is this one, right? And spread of data along feature f2 is somewhere this one. So it's clearly visible that spread of data along feature f2 is wider as compared to spread of data along feature f1. So I will drop my feature f1 and keep feature f2. But why will I drop? So I will drop feature f1 and keep feature f2, because by dropping feature f1 I am losing very little information of data, and by keeping my feature f2 I am preserving the more information of data, right? This is the whole principle behind the mathematical formulations of principal component analysis, right? Let's take a bit complex example, and X is our data matrix with n data points. It's a two-dimensional data with column standardized, right? Column standardized meaning the mean of feature f1 is equals to mean of feature f2 equals to 0, and standard deviation along f1 is equals to standard deviation along f2 equals to 1. right? Now let's draw this data points. So let's see our data points look something like this. Right, and this is our feature f1, this is our feature f2. Now if you see the spread of data along feature f1 and spread of data along feature f2, these two are wide enough, right? So we can't simply drop feature f1 and f2, right? But if you see, there's one direction, this along which the spread of data is wider. Let's call this direction as f1 dash, and let's draw one more direction which is perpendicular to f1 dash, and let's call this as f2 dash, right? So the spread of data along f1 dash is way much wider as compared to spread of data along f2 dash, right? Now if we can find the direction of f1 dash and f2 dash and drop f2 dash and project all our data points on f1 dash, then we will be able to convert our two-dimensional data points into one-dimensional data points, right? So in very English terms, in very plain English terms, we want to find the direction of f1 dash such that the variance, or you can say spread, of projection of all data points on f1 dash is maximum, right? And this is what we will use as a base for our mathematical formulation. So we want that if we project all this data points, if we project all these data points on f1 dash, then the spread or the variance of this projection along f1 dash direction should be maximum. Okay, so now we will see the mathematical formulation. Right, so we want to find the direction of f1 dash. Let's call f1 dash as u1, because all the articles and books refer f1 dash as u1, and I don't want to find the whole line of a u1. I just want to find the direction. I just want to find the direction of u1. and direction of u1 direction of any vector is represented by unit vector. So the magnitude of u1 will be 1, right? Now I will list down some mathematical terms which will be useful in our objective functions, right? So let's say f1 is f2 and this is the direction of u1. Let's consider one data points which is xi, and projection of xi on u1 is, let's call it as xi dash, right? So D is set of all the data points of xi's where I goes from 1 to n. D dash is set of all the xi dash where I equals to 1 to n, where xi dash is projection of xi on u1, right? And this can be written as u1 into xi divided by u1. This is coming from linear algebra. Now we know that our u1 magnitude of u1 is 1, so this will be simply u1 into xi. Now in terms of dot product, it will be u1 transpose xi, right? So xi dash is nothing but u1 transpose xi, right? If I want to find the mean of x1 dash, which is mean vector of xi dash where I equals to 1 to n, it can be written as u1 transpose of x bar, and x bar is mean vector of xi, I equals to 1 to n, right? Now we want to, so our task in hand is find direction of u1 such that variance of projection of all data point on u1 is maximum, right? So variance of projection of xi in the direction of u1, this can be written as average of 1 to n, how much each data point is varying from the mean, right? Which will be equals to u transpose xi minus u transpose x bar, the whole square. Now since we have assumed, since we have column standardized, then x bar will be on origin, right? So this term will be a vector of zeros. If we have n vectors, this will be n times 0. Variance of projection of xi on u1 can be written as 1 upon n I equals to 1 to n u transpose of xi, right? Now this is what we have to maximize. This is what we have to maximize, right? So our objective function can be written as find u1 to maximize xi, right? There will be one constraint, and the constraint will be equals to 1, right? That you might I just want to find out the direction of u1, right? That's why this is a unit vector. And what if I don't consider this constraint? What if I don't consider this constraint? Then I will get my direction of u1 as infinity comma infinity, right? I mean, then there will be no feasible solution. There's no bounded solution, right? No solution. That's why we need the constraint. Okay. In the last video, I told you guys that I will explain why we need the column standardization, right? The first thing, column standardization need when all the features are not in same unit, right? So for example, income can vary a lot, right? Income, let's say if I have a two feature, one is income and one is interest rate, right? Income can vary a lot, but interest rate vary a little, right? So in that case, my u1, if I try to find out this direction of u1 without any column standardization, what will happen? It will give more importance to my income, right? Even though the interest rate, it doesn't vary a lot, but it is explaining my data quite a bit, right? But it will give very less importance. So my u1 will give very less importance to interest rate if I don't change the scale, right? But if I change the scale, if I column standardize it, then what will happen? They both will be on the same scale, right? So this both income and interest rate, let's call it as R, will be on same scale. So in this case, my u1 will give equal importance to both while optimization, right? So we don't want the unit to play a role while finding the direction of u1. That's why we do the column standardization. In very simple terms, we do not want unit of feature to play any role to decide the direction of u1. That's why we do the column standardization. Okay, thank you.